The objective of this lecture is to provide the first part of the description of the orbit in space, and in particular, to focus on coordinate systems and the definitions of the orbital elements. This lecture will be divided into the following parts. First, we will provide coordinate systems that form the foundation of describing the orbit in space. These coordinate systems are the heliocentric-ecliptic coordinates, and the second are what are called Earth-centered inertial coordinates. Now, using these coordinate systems, we are going to develop what are called the classical orbital elements. And these are just often called the orbital elements, but the full term is the classical orbital elements. Now, these orbital elements provide a description of the orbit in a geometric way. So in particular, we're going to describe the following quantities, which are the semi-major axis, the eccentricity, the longitude of the ascending node, the orbital inclination, the argument of the periapsis, and finally, the true anomaly. Now, these 6 orbital elements are going to be shown eventually to be equivalent to position and velocity. In other words, if we have position and velocity, we can get the classical orbital elements, and vice versa. We can go from the orbital elements back to position and velocity. And this lecture is going to focus on a description of all these orbital elements, and we're going to use several geometric constructs in order to be able to make that happen. So we will actually go through all of this in this lecture, and then subsequently we will come up with ways to be able to compute these quantities. But this lecture is actually going to focus on the geometry of an orbit using orbital elements. So let's start with coordinate systems. The first of these coordinate systems that is of importance is what is called heliocentric-ecliptic coordinates. Now, as the name heliocentric would imply, this is a sun-centered coordinate system. So the way this works is as follows, is that nominally, and when I say nominally, what I really mean is approximately, the planets in the solar system move in an inertially fixed plane. Now, this inertially fixed plane is called the plane of the ecliptic. Or, equivalently, the ecliptic plane. Now, we can do this for any planet, but we're really focusing here on the Earth because that's, where everything we know occurs. So we're going to deal with the Earth. So consider the motion of the Earth relative to the sun. Now, this motion of the Earth relative to the sun can be viewed as follows, is that if we have the motion of the Earth basically moves in a circle, right? So the sun is in the center of this circle. Now, the Earth is somewhere on this circle at some point in time, right? So here's the Earth. And I can call the radius or the distance from the sun to the Earth, if this is moving in a circle, I'm going to call it RSE, which is the sun-Earth direction, the sun-Earth line, and that's the radius. So this is the motion. Now, you can see that this plane in which the Earth is moving, this is what's called the ecliptic plane. Now, the ecliptic plane, together with various points in the motion of the Earth relative to the sun, can be used to start defining an inertially fixed coordinate system. So the ecliptic plane itself is inertially fixed. So that's the first thing. We assume that that's an inertially fixed plane. But in order to be able to see how to start defining coordinates that are actually useful in being able to do calculations relative to a planet, because ultimately we're going to be doing things relative to a central body, and that central body is going to be nominally the Earth. It could be any body, but we're focusing again on the Earth. We could be dealing with another body. We could be dealing with the sun. We could be dealing with another planet. But all of the same concepts apply once we've established how to do this relative to the Earth. So the first thing we're going to do is we're going to establish a coordinate system, which is called this heliocentric-ecliptic coordinate system, based on this motion of the Earth relative to the sun. So we're going to start with an alternate perspective of the motion of the Earth relative to the sun. And this alternate perspective is going to be developed as follows. So first, imagine that I have kind of a angled or three-dimensional view of the motion of the Earth relative to the sun. So in this diagram that I've drawn, the sun is in the center of this diagram, and this sort of what looks like an ellipse, but is actually a circle, is the orbit of the Earth. So here's the sun. Now I'm going to mark 4 particular locations on this diagram which are of importance. The first one is going to be this point right here, which I'm going to draw the Earth as sort of a sphere or a circle, and I'm going to draw this is the equatorial plane of the Earth, and then this normal to it, which is the axis of rotation of the Earth. And then directly opposite that, I'm going to draw the exact same thing. So these are 4 different times of the year where I'm interested in the location of the Earth. So there's the second location, and then I have the third location, which is going to be off to the right and off to the left. So if I draw that off to the right, I have the location of the Earth at this point, and then if I draw off to the left, I have the location of the Earth at this point. Now these 4 points that I've drawn are not random by any stretch of the imagination. They're actually quite well defined. This point right here is the first day of spring. And then, of course, if I kind of go around the circle, this point right here is the first day of summer. And then the point at the bottom is the first day of fall or autumn. And then this last point here is the first day of winter. Now, the reason I started with the spring is because the zodiac actually starts with the spring. So on the first day of spring, this is when the Earth enters Aries. So this is actually what's known as the first point of Aries. And it's the first point of Aries because it's the first instant at which the Earth is in the constellation Aries. Now, the direction from the first point of Aries through the sun, if I actually draw that direction going straight through to from the Earth to the sun on the first day of spring, that direction is actually defined as it's the symbol Aries. It's the ram's head, and this is actually what's called the line of Aries. The line of Aries is exactly that. It's the direction from the Earth to the sun on the first day of spring. And we actually define the unit vector in that direction. So this unit vector is actually defined as x with an epsilon. That's the direction of the line of Aries. And so the unit vector in this direction is actually x epsilon. Now, the direction y epsilon is actually the direction that is such that z epsilon points in the direction of the axis of the rotation of the Earth's orbit. If you think of the Earth going in a circle, it has some angular velocity. It points in the direction of that angular velocity. But the one I'm really interested in is this direction x epsilon, because x epsilon provides for me the key inertially fixed direction. Because remember, this is the ecliptic plane, and we've assumed that the ecliptic plane is inertially fixed. And as a result of it being inertially fixed, if I freeze the motion of the Earth to be at the first day of spring, which puts me at the first point of Aries, that direction from the Earth to the sun on the first day of spring is also inertially fixed. So it means that x epsilon is fixed in what I'm calling the inertial frame. Right? It has to be, because the ecliptic plane is inertially fixed, and I freeze it at some point in time, and that point in time provides for me a direction, and that direction must be fixed in the inertial frame. So that gives a way to be able to start this description of being able to develop an inertially fixed coordinate system for motion relative to a planet. Now, just to finish this discussion, this direction, which is normal to the ecliptic plane, is z epsilon. So if I take z epsilon crossed with x epsilon, I get y epsilon. And so y epsilon has to point in the direction from the sun to the Earth on the first day of winter. It's actually opposite the direction that you would think of when you think of x epsilon, which goes from the Earth to the sun. This one points from the sun to the Earth. But that is our inertially fixed coordinate system, which gives us the heliocentric-ecliptic coordinates. Now we're finished with that, and now we're going to move on to Earth-centered inertial coordinates. So now let's talk about Earth-centered inertial coordinates. And these coordinates are often referred to as ECI. Abbreviate them as ECI. Now, these coordinates are Cartesian coordinates, and we're going to describe them as follows. Again, the Earth is tipped. Its axis of rotation is not normal to the ecliptic plane. So here's the axis of rotation of the Earth. This is the spin axis of the Earth. The top part of this is the north celestial pole. And then the other side is the south celestial pole. And then we have the equator of the Earth. So the equator of the Earth looks as follows. So this is the Earth's equator. Now, if we freeze the motion on the first day of spring, the direction coming out of the page in this diagram, this is x epsilon. That's the same direction. That direction never changes. As the Earth moves around in its orbit, x epsilon is always the unit vector that points in the direction along the line of Aries. The line of Aries, remember, is defined at an instant of time, but that never changes. If I move off to this direction, if I just point in that direction, this direction is to the sun. So what I mean is that the Earth is moving in this orbit, and I'm always pointing in the direction to the sun. Now, this actually provides for me a way of being able to develop a coordinate system that is now fixed in the Earth. So I'm going to use x epsilon as the basis, and I'm also going to use the North Pole. So if I sort of rotate this picture such that the axis of rotation points in the direction that is sort of up in the diagram, if you want to call it that. So we're just going to rotate it back. We wind up with a picture that looks as follows. So here's the Earth, and then here's the equator of the Earth. And then this direction, which is inertially fixed, that direction is going to be called Ix, and it's equal to x epsilon. It's the same direction. It's x epsilon. Now, this direction is the North Pole, which I'm going to call Iz. So this is along what I called in the previous description, the North Pole. So this is along the North Pole of the Earth, of course. And then this direction Iy completes the right-handed system. So Iy is equal to Iz crossed with Ix. Now the Earth, of course, is moving in its orbit. And this point right here is the center of the Earth, which I'm going to call O. So the spacecraft is somewhere out here. It doesn't matter where the spacecraft is. I'm not interested in the spacecraft right at this point. But this coordinate system, O, which is the center of the Earth, together with Ix, Iy, Iz, that's what's called ECI coordinates. So O, together with the basis Ix, Iy, and Iz, these are what are called Earth-centered inertial. And it's important to understand it's not just Earth-centered inertial, but it's Earth-centered inertial, and they're Cartesian coordinates. So now I have a way, if I have a spacecraft, I have a way of being able to determine the position relative to the center of the Earth. And we're going to assume, and this is the last part of this, is that it's assumed because the Earth is moving in this large orbit relative to the sun, so its acceleration relative to the sun is quite small. So we're going to assume that the center of the Earth is inertially fixed. It's not inertially fixed, but we're going to assume it's inertially fixed. And that's because the Earth moves very slowly. Because the acceleration of the Earth is small. And since it's small, we're just going to neglect it. That's basically what we're going to do. So now we have a way of being able to describe the position of a spacecraft relative to the center of the Earth in terms of an inertially fixed coordinate system. So then, the position of a spacecraft relative to center of the Earth can be expressed in Earth-centered inertial coordinates. And again, remember, these are Earth-centered inertial Cartesian coordinates. As we're going to say r of s relative to O, which I'm just going to define as r, is going to be x ix plus y iy plus z iz. Now, given that this basis is inertially fixed, that implies that the inertial velocity is equal to x dot ix plus y dot iy plus z dot iz, which will be referred to as vx ix plus vy iy plus vz iz. So what that means is, if I say let, I'm going to use this base. I'm going to say I is equal to ix iy iz. Then that means that the position expressed in I is equal to x, y, and z, and the inertial velocity, again expressed in I, is equal to vx, vy, vz. Now this starts the description of the orbit in space. So first what we've done is we've described the position and velocity in terms of this Cartesian coordinate system, which has its center, its origin at the center of the Earth, and it's inertially fixed, and we get these 6 quantities. So we have six quantities, 3 that describe position and 3 that describe velocity, and they are in a Cartesian coordinate system. So we're going to use the ECI descriptions, let's say expressions if you don't want to say descriptions, expressions of R and VI to formulate a description for the orbit in space. And that's what we're going to do next. So now let's talk about the orbit in space and we're going to do this in terms of what are called classical orbital elements. So in order to be able to do orbital elements, we need some geometry. So the way we're going to start this, and it's kind of a natural way to do it once you've understood a little bit about rigid body kinematics, but the orbit, which we'll just take as an ellipse at this point, is a rigid curve. What that means is that any 2 points on this curve are a constant distance from one another, right? In the case of an ellipse, or an elliptic orbit, this curve is closed. Because it's periodic. So what we can do is we can sort of draw this diagram, and this diagram will help provide a starting point. So this curve, which is this orbit, is somehow oriented in space in some way, right? So I'm going to draw this ellipse. Here's my ellipse. Now, I don't know what its orientation is relative to this basis ix, iy, iz. All I know is that somehow this orbit sits here, right? And there's the point O, which is the center of the Earth. Now there's the closest point on the orbit. Now remember, the closest point on the orbit is the periapsis. So there's the periapsis, which means that the direction from O to P, which is what we had described when we did the two-dimensional version of the orbit, that direction, or that vector, what lies along that direction is the eccentricity, right? We also know that normal to the orbit plane, we have this vector, which is the specific angular momentum. And these two vectors were what were used to be able to describe this coordinate system, which we called px, py, pz, which had px along E and pz along H, and then py was the cross product. But we're not going to be doing that right this minute. What we're going to be doing now is we're going to be describing this location right here. There's the spacecraft. And remember that this vector is the position, which is the one I just defined, and the angle from E to R, which we had defined before, was the true anomaly. So somehow we have to be able to get a description of this orbit in terms of quantities that make geometric sense. And these 6 quantities that we're going to use are what are called the classical orbital elements. So the classical orbital elements provide a geometric description of the orbit of a spacecraft relative to the inertial frame. So relative to I. What I mean by that is the orientation relative to this basis ix, iy, iz. So now what we're going to do is we're going to actually start defining these 6 orbital elements. So here are the classical orbital elements. The first one is what's called the semi-major axis, which some of these we've already developed earlier, but we have to go through all 6 of them because they all kind of work together. The second one is what's called the eccentricity. Now these 2 orbital elements together provide the size and shape of the orbit. The semi-major axis provides the size, the eccentricity provides the shape. As we saw before, the eccentricity tells us what kind of orbit it is. The third orbital element is what's called big omega, and it's known as the longitude of the ascending node. The fourth orbital element is called I, and it's the orbital inclination. The fifth orbital element is called little omega, and it's the argument of the periapsis. And the sixth orbital element is nu, which is the true anomaly. Now, when we did the two-dimensional description of the orbit, we did 3 of these. We did A, E, and we did nu. But we didn't do the middle, these 3, 4, and 5. These right here are a way of being able to provide the orientation of the orbit in space. Because without that, we have no idea what the alignment is of all these quantities on the orbit. So we need to know the orientation of the orbit in space. Now it turns out that omega, I, and little omega together form a 3-1-3 Euler angle sequence. And that allows us to be able to use Euler angles as a foundation for being able to describe the orientation of this orbit in space. Remember, what we're doing is we're orienting the curve, which is that orbit. In this case, we're talking about an ellipse, but we could equally be talking about a parabola or a hyperbola. In this case, we just happen to be focusing on an ellipse because it's just easier to draw it. But this description pertains to all of them. It doesn't make a difference what kind of orbit it is. So these are the 6 orbital elements, and now we're going to provide a little bit more of a description of what these orbital elements actually look like by imposing on the diagram the angles to be able to show what this information looks like geometrically. So here's more geometry of the orbit in space. So once again, we have these directions Ix, Iy, and Iz. And here's our orbit. Now, this direction, which is the closest point on the orbit, or that vector, which that point there is the periapsis, that direction is the eccentricity. Once again, since this is the center of the planet, or the Earth in this case, this direction is the direction of the specific angular momentum. Now what I'm going to do is I'm going to draw some new vectors here, which will enable us to be able to describe these orbital elements. The first one of these vectors is the vector Iz crossed with H. So Iz crossed with H is going to be called N. So N is equal to Iz crossed with H. Now you'll notice that because I've taken the vector product of Iz with H, Iz crossed with H has to be orthogonal to Iz, which means it has to be in the Ix-Iy plane. This vector is what's called the line of nodes. And this point on the orbit that is along this vector n, this point is what's called the ascending node. Now I'm assuming in this picture that the orbit moves in the direction of the arrows. It's called a prograde orbit, or a positively moving orbit. And the angle between Ix and n, that angle is what's called the longitude of the ascending node. So omega is the angle between Ix and n. I'm going to put all this in a more detailed description later. But this point where the orbit crosses the line of nodes is what's called the ascending node. The angle between Ix and the line of nodes is the longitude of the ascending node. The next angle is this angle between Iz and H, and that is the orbital inclination. And then lastly, before I get to the true anomaly, the angle between N and E, that angle is the argument of the periapsis. And then the spacecraft, of course, is here, as I've denoted. And then this is the position, which makes this angle the true anomaly. So that angle is nu, which is the true anomaly. So this combination of angles, omega, little I, and little omega, so big omega, little I, and little omega, is what forms the Euler angle sequence. So let's go into a little bit more detail on these angles. So omega is the angle between Ix and n, where n is equal to Iz crossed with Hi. I is the angle between IZ and HI. And finally, little omega is the angle between N and E. And of course, the true anomaly is the angle between E and R, but we already know that, right? So that's been defined earlier. So these are the three angles that I'm focusing on. These angles are the ones that form a 313 Euler angle sequence. So this is a 313 Euler angle sequence. So the last part of this description, at least for now, because we're not focusing in this lecture on how to compute these angles, we're only focusing on what these angles are, is we're actually going to draw some pictures to show how this actually works. And we'll start with the ellipse in its original orientation, and then we'll go through these different rotations to show this 313 Euler angle sequence. So now let's describe this 313 Euler angle sequence. Omega I little omega. So what we're going to first do is we're going to draw this ellipse. So here's that orbit. Now, this is the focus, which is, of course, the center of the planet. This direction right here is IX. This direction is IY, and then IZ is out of the page. This is before I do any rotations. And now I'm going to perform that first rotation. So when I perform that first rotation, my ellipse goes into this configuration as I've shown here. Now, when I'm done with that, this direction, if I draw the full direction, that direction is actually n. And I'm going to call the unit vector along that direction n sub x. N sub z is the same as iz because I'm rotating about the z-axis, which makes this direction ny. So that's the first rotation. The angle of that first rotation is this angle here, which is omega. So that's the longitude of the ascending node. That's the first rotation. The second rotation now picks up where the first rotation left off. So the second rotation is a 1 rotation, right? Because it goes 3, 1, 3, which means the second rotation has to be about this direction n sub x. So if I now look at n sub x, and I say it's out of the page, so this is now the second rotation, then that means that n sub y is this direction, as I've shown here, and n sub z is this direction. But now I'm doing a positive rotation about the direction n sub x, which means that I get a new orientation of this orbit. I'm going to call this direction qy, and I'm going to call this direction qz. And of course, that means that n sub x has to equal q sub x, which is my new coordinate system. Now, that basis, once I've performed the rotation, that angle is the orbital inclination. So that's the second rotation. Now, the third rotation is a 3 rotation again, so it's got to be about qz. So the third rotation, if I draw it here, here's qz. Now, in order to be able to preserve this rotation properly, this direction is going to be qx, and then this direction is going to be qy, because qz crossed with qx is qy. And the third rotation is by this angle omega, which puts me into this final orientation, which is px, py, and then this direction is pz, and this angle is little omega. Now, in going through all this, px, py, pz, these vectors form what I had defined earlier as the perifocal basis. Now, what that means is that when I'm all done doing all these rotations, this is what I have when I'm finished. So after performing all 3 rotations, so the 3 rotations, omega, I, and little omega, we have this ellipse that's, again, back to the picture that we had before. And this basis, this direction, is the eccentricity. This is px. This is py. And then pz is the direction out of the page, which is also in the direction of the specific angular momentum. If I draw that in 3 dimensions down here, here's what it looks like. So this again is point O. Here's my ellipse. And this point right here that passes through along the direction of the eccentricity, that's the periapsis. That's this point right there. That's the periapsis. This is the eccentricity. And these 3 basis vectors are px, and then pz is along the specific angular momentum. So this direction is pz. And then if I take pz cross with px, I get some direction out here, which is kind of hard to draw in 3 dimensions. But that direction is py. And then the spacecraft is sitting here. And this angle is the true anomaly. So that's, if I put the spacecraft on this 2-dimensional picture, there's that position, and this angle is the true anomaly. So that completes a description of the orbital elements. So we have a complete picture now of what these orbital elements look like. Now that we have a picture of the orbital elements, we can actually use them to do calculations in the future. Right now, we were just trying to describe geometrically what the orbit looks like. We're not actually going to go through and show how to do all the computation. That's a fairly lengthy and involved process. And before you can get into doing it, you have to understand the setup of these angles to be able to understand, what to do when you actually do the calculations. So that takes us to a summary of this particular lecture. And to provide an overview of what we did in this lecture, the first thing we did was we discussed coordinate systems. And these coordinate systems enabled description of the orbit in space relative to an inertially fixed set of coordinates. The first ones of these coordinate systems was heliocentric-ecliptic coordinates. The second one was Earth-centered inertial coordinates. And these coordinate systems, especially the second one, enabled us to be able to describe the orbit in space using classical orbital elements. And in particular, we described the semi-major axis, the eccentricity, the longitude of the ascending node, the orbital inclination, argument of the periapsis, and finally, the true anomaly. And what we did in the process of describing these was we focused on the fact that the three angles, the longitude, the ascending node, the orbital inclination, and the argument of periapsis, formed a 3-1-3 Euler angle sequence. So we actually described the 3-1-3 Euler angle sequence. So with the focus being on those three angles, we described the 3-1-3 Euler angle sequence omega, little I, and then little omega. And we're going to use the material that was studied in this particular lecture as the starting point for being able to develop the transformations that we can use to compute orbital elements given the ECI position and velocity, and vice versa, the computations that we need to perform if given the orbital elements, we can compute the ECI position and velocity, and that will be done in the subsequent lectures. But this lecture is going to stop here because that gives us a complete geometric description of these orbital elements, which can now be used for the next phase of the study.